Cool. So for those who don't know, I'm Molly.
Hi, I'm Michael.
We're going to kind of tag team through this presentation. Hold on. One more technical difficulty. Okay, there we go. So this is kind of what we're going to go over. So the roads that brought us to JPL, each of us, and then the 2020 Rover Perseverance, that should have been called Hindsight. We just went to Florida to watch it launch, and we both were involved in helping it to go in different ways. So we'll give mostly an overview on what it's going to do, what it's done, that kind of thing. And, you know, we'll talk a little bit about what we've done, but it's not so much about our work. And then a little bit, you know, spread throughout about what it means to like send a spacecraft during a global pandemic. And then some time at the end for questions. So, but interrupt us if there's things along the way. Okay, so this is overwhelming because that's kind of my personality. So, so I'm a 589 alum. I was in CV from 2008 to 2012. I was involved in robotics when I joined in 2008. It was a much smaller team, and I also knew how to do nothing, like legitimately nothing. I had never used a hammer. I'd never used a power tool. I had never thought about coding, and I still don't think about code because, you know, that's not for me. Sam's got it all. And it was an experience that changed my life, that sent me towards science and towards engineering. So while I was there, I was just a member. I was a very, very nervous freshman when I first joined. And then by the time I realized I could be comfortable, and Amy, who you guys all know, part of the group that's putting this whole thing on, when she joined, then we both worked as spirit chair when we were juniors. And that was just a title that Dr. Neat gave us so that we would stop bugging him. And it was essentially, we were just cheerleaders all the time to try and get more people to join, to get, you know, more excitement when we were in the stands. A little bit of 589 history, and for all of the alums, since this is an alum event, I included a couple photos in the backup slides. Just as I was digging through my stuff, you know, we have some young Thomas, some young Sam, Tanner with 589 written on his stomach. So, you know, the classics. But yeah, so when I joined, it was a little bit different, a lot of it different. It was still trying to build robots in 6 weeks. But there were hardly any women on the team, and we were much smaller. So shout out now, and then shout out, you know, at every point forever to Lynn for growing the team and making this such a wonderful, wonderful team. Okay, so I'm gonna kind of just run through the rest of life, since the main point is 589, everything else is just gravy. So I went to Allegheny College, which is a school smaller than CV. I studied physics, and I minored in dance and movement studies and astronomy. I was part of a sorority, Alpha Chi Omega, where again, I was pretty much just like a fancy spirit chair. I was in charge of recruitment and philanthropy and a few other things. I did a lot of dance while I was there, and the physics capstone on the temperature effects photovoltaics and the dance capstone on movement therapy for adults. Those two were involved in the conversation that helped me get a job at JPL. So as a funny story, and kind of like the route that got me into JPL, was when I was a junior going into senior year, I was doing photovoltaic research at my college, and I was stuck and I needed help, and my advisor was traveling and I had no idea what to do. So what else do you do but call Lynn? And Lynn offered me like a walkthrough through the power group at JPL. I met some really, really awesome, amazing people. And aside from being blown away, they kind of changed how I was thinking about my problem. And then fast forward to graduation, I was hired by one of the people that I met that I asked for help. And in talking to him, about hiring and something that students can keep in mind as they go to look for jobs, especially in such a weird world that we're living in today. What you study and what you do is the most important, hands down, but don't forget to be a person. So when I did the dance capstone that we were talking about, the man who hired me asked me to send him a copy of that so he could see how I wrote, and that helps in writing test procedures and writing science documents and things like that. And it also helped in my understanding of groups. So those are both things that the hiring manager was looking for. And then super quick, we're going to talk a lot about Mars today, but I've been lucky in my 4 years of being there. I've worked on solar cell characterization. So when we're in low intensity, low temperature environments like flying by Jupiter and stuff. I've worked on operations for Dawn, where I was a power subsystem engineer. I had to do that awful coding stuff, and it just sucked the whole time, but Dawn was pretty cool. Most recently, I worked on Sherlock, and I'm still kind of working on Sherlock. That's one thing we're going to talk about. SMAP, another operations thing, and then Europa Reason, Europa Clipper, and outreach stuff.
All right, so hi everyone, I'm Michael. I was briefly a mentor in the last season, going over some of the holistic stuff, and looking forward to being a lot more engaged this upcoming season. So, bit of a convoluted path to engineering, but I was going to cover some of it, not related to CV, unfortunately, but hopefully I'll have some times along the way. So I was born in the US, but my parents are actually French and Caribbean, so I grew up in Antigua in the Caribbean and France most of my life. Started high school back in Paris at EABGM, which in French stands for École Active Bilingue Génie Manuel. That's where I started off. For a pretty random sequence of events, it turns out that I actually started studying business before engineering, very different path. Sort of had to help my dad at the time with his business. Learned some interesting things, hated it, absolutely wanted to change. One of the things to know with the French system is that it can be very strict and unforgiving. So if you haven't decided by age 16 that you're going to go for science, you almost have no chance of going in science. So along the way, you would hear things like, why do you ever want to become an engineer? You'll never be one. You didn't succeed when you were 16. What makes you think you can qualify now? So, if there's anyone out there that kind of, wants to go on a different path and hears a lot of these negatives, I strongly invite you to at least challenge it and, give it your own try rather than take it face value from other people. So that was one of my biggest lessons learned along life. And if you take anything from today and it's just that, I'd be very happy, and I would consider I fulfilled my role. But now the nice thing is I was kind of in this weird program where you get to move around, and essentially every 6 months to a year, you change countries for up to 6 months or a year. So I started off in Paris at the ESCE, which is École Supérieure de Commerce Extérieur, which is a French business school. That's that picture on the top left with that weird cone-shaped building, which was our library. Studied in Holland and Rotterdam for about a year, was working in Miami for a year after that, and then was in Japan in the Osaka region for the year after that. Why I'm mentioning this is, like on some of these big projects like Mars 2020, it's of course a great American achievement, but it's easy to forget that there's a lot of work that happens with allies as well. There's a lot of instruments that come from France, optics from Korea or Japan, somewhat from Germany as well. So, on these big projects, if you're either considering college or already in college and you have one of those opportunities to go study abroad, I highly encourage you to do that. Because, there's a good chance you might be working with people from other countries who might think differently, have different priorities, different perspectives, and it does make it smoother, and it is nice when you can understand the people on your team. So that was even though I was trying to actively go away from business, that was still a pretty great thing to learn, and I'd encourage people to do that. After that, I went to University of Miami. I was doing an MBA at the time, but that was kind of my foot in the door towards getting in the American system and starting back towards science and engineering, so kind of working part-time and taking science classes, which eventually led me to USC after that. That's why I was studying astronautical engineering from a bachelor's as well as chemistry. I just really could not pick a field. I was interested in both. To me, science and engineering are kind of not these nebulous fields, but I hate compartmentalizing them. So I kind of always wanted to do everything. It's horrible. I could never decide. Even today, sometimes I'm still not sure what exactly I'm doing, but I just like to combine as much things as possible. So I picked both and ran with it. I was doing part-time studying, part-time work, either in the rocket propulsion lab or for one of those electric photocatalytic labs. It's a mouthful. We're trying to see if we could convert CO2 through solar power for either scrubbing purposes or making oxygen. So yeah, that was pretty interesting work. I'm a big fan of Taekwondo, so both at Miami and USC, I joined the team. You can see me on the right. I was one for the UCLA tournaments, friendly tournament. So that was a lot of good time. And you get busy sometimes. Don't forget to also do things you love on the side. After that, I took a little break while at USC to go work at Ames for a little bit. That's actually where coming from Ames to visit JPL, I actually met my mentor, who then I ended up working with at JPL. That's kind of what got me transferred over to JPL. At that time, I was doing earth science. It was a project called HITEST for spectrometry, airborne spectrometry. So we'd load our science equipment on planes, go airborne, and then test it up in the sky and try and get feedback for data to enhance the calibration. And then after that, through that first work, I ended up at JPL and then ended up in another group. So, sometimes if you do an internship, you might end up in a path where you didn't think, but, it's create those contacts. Don't be afraid to try and explore other things. Again, I was in like an earth science group, but then I ended up in propulsion, which I had an interest for, but yeah, that's kind of the how I ended up getting at JPL. And then eventually in the propulsion group, as I was working on different tasks, I just kind of got enrolled in that and eventually switched over completely after a while. Like I said, we'll be talking about Mars 2020. For the most part, I ended up working on quite a few varied things at JPL that I was happy to take a part on. One of them was HITEST. So I'm now working as a propulsion systems engineer there. Several of the missions inside that you might have heard about recently, Mars 2020, of course, that we're going to talk about today. Some other cool projects, one of which I was working with Thomas actually here, which is a solar thermal propulsion. So it's a great pleasure to work with you on that. It's still ongoing, by the way. Open to publish, so I got to email you about that actually. Europa Clipper, there's a lot of missions for Europa that are sort of up and coming that are pretty exciting. Europa Clipper is the official one. Europa Lander is still in the works, not an official mission yet, but people are still working on that, so that'd be very exciting when that happens. I won't say if, but when that happens. And of course, coming up after Mars 2020, and we'll tie into that, is the sample retrieval lander, which is sort of what comes next after Mars 2020, and there's also some pretty exciting stuff there, and other little tasks here and there. So, yeah.
So this is just like a quick, we just kind of want to show off some cool pictures that we have. So again, we got to go and see Perseverance take off. So we flew to Florida. It was crazy. Although not nearly as crazy as either of us expected. Like, I don't know, I assume that most people haven't been traveling, and I'm not recommending traveling during a global pandemic. But while we were at LAX, it was like a ghost town. It was the weirdest thing we've ever seen. And our plan while we were over there was just kind of shack up, stay inside, and then go watch the launch. And that's what we did. So on here we have over on the left side, left corner, we're checking out the entryway to the beach where no one was to try and we had to stake out a spot the day before to see where we were going to watch the launch. It could be away from everyone. The pictures, those bottom two on the left side, those were in 2012. I went to watch the launch, and we got to be so close. We got to be at KSC. It was super fun. And this time it was just not quite the same. So over on the right side, Michael and I down at the bottom, that's as close as we could get to the launch site. So we were in like a little private area of the beach, but it was not in the viewing area that KSC has. KSC is Kennedy Space Center. And the one in the top right corner is the fam hanging out on the beach. We're watching NASA TV on the phone and, you know, watching the rocket go off on the other side. So it was a little bit different. Oh, and most important, the space food down at the bottom, that thankfully my little sister is very, very crafty. So she made like a tiny little party for us on the beach. But it was very weird and it was very different, but we still got to see our hardware head off, and we got to see, you know, it in the museum at Kennedy Space Center, which was pretty cool. Oops.
I think it's probably one of the coolest parts. I think it'll talk about that is, you know, seeing your work in an exhibit.
Mm-hmm.
It's quite fun.
We have, for anyone that's like friends on Insta, and if not, you're welcome to friend on Insta. We have a walkthrough of this picture on the right side. We have a walkthrough of the whole Mars display that they have, you know, starting with the Pathfinder, some of their concepts, and leading all the way up to Perseverance. It was super cool. And aside from, you know, the awesome moment of realizing that you're sending something to space and it's so cool, I was in tears the whole time, and which is common for me. Like, you know, commercials come on, I cry, but this one was different. But to see everything, you know, everyone that goes to CD is very, very lucky to be so close, you know, to not just to JPL, but to have, you know, groups like 589 that encourage you to go out and learn. So a lot of what we saw in the museum were things that we got to see that I was lucky enough to see growing up. And so it was just a very, very nice experience. But the emotional stuff aside, now we'll talk a little bit about Perseverance, or a lot of it about Perseverance. So quick overview. We launched on the 30th. We were seconds ahead of what we should have been, and that threw everybody off, but you know, it was fine. We also had an earthquake that woke everybody up so that they could watch the launch in case they weren't awake, because even Mother Nature wants you to be involved in science. We plan to land on February 18th around 3:40 California time, and the mission is expected to take, or is required to take, at least one Martian year. So 2 Earth years, pretty much. The main purpose of what we're doing, what this rover is going to be doing, is we're going to be looking for habitability, seeking biosignatures with one of the coolest instruments. We're going to cache samples in one of the most impressive pieces of architecture as described by the 2020 team with the sample caching system. And then we're going to prepare for humans. So all of the instruments, which we call payload, there are 7 instruments on board, and all of those are targeting this purpose. So for any of the students who will be coming back next year on 589, when we go and we say, like, you know, our level 1 requirements are build a robot. Our level 2 requirements are build a robot that moves, that kind of thing. What this says is that this would be like our level 1. This is our purpose. This is what we need to do. We need to be there for 1 Martian year. We need to cache samples and do these items. And then they flow down, you know, to everybody else involved. But it's based off what 589 does is the same system that JPL does. And quick current status. So when we launched, we had a really, really rough time. So not really, really. It was like kind of rough, but we were prepared for it. So we immediately went into a safe mode when we launched. We made it like minutes up, and then there was an error on one of the heaters, and that threw us into safe mode. So before we could even really do anything, while we were still chugging along, the onboard computer already had to do a lot of rework and switching and everything. So part of thinking about the failures that are going to happen and, trying to test for everything that you ever could need, when you fail, are you going to switch from RCEA to RCEB? Testing those kinds of things, that came into hand like immediately. So test. Okay, so the current status is right now we're cruising and we're about 35 million miles on a just under 300 million mile journey. Our one-way light time is just over 20 seconds. So that means we send a command and it takes 20 seconds for the spacecraft to get it. And it takes 20 seconds for us to receive it, and that's only going to get longer. So it's also, there isn't kind of the immediate, you type something in, hit enter, you get a response. There's a good amount of anxiety built into any kind of spacecraft.
How long is that from Earth to Mars itself?
This is, from us to the spacecraft. So,
right, but do you know how long it is from Earth to Mars?
It's variable as we move closer and farther and things like that.
Roughly 7 minutes, I guess, like your average. It kind of depends, but roughly 7 minutes.
Yeah. Cool. So,
whichever. Unless you were going to show a cruise stage. I can just show some of that.
Yeah. Okay, yeah. I'm going to open this link. Tell me if you can see this. Maybe if you could see it. So the NASA website has some really, really awesome tools. And if you haven't already gone and checked it out, then as soon as you're done here, go check it out. So we already went over the launch. This is our cruise. So this is what our little capsule looks like. It's the cutest. These are the solar panels on the back. They're just adorable and super, super helpful. Let's see, where are we? Okay, so this is where we're at. This is where we're going. As it loads, sorry for my internet. Okay, so this is the heat shield part of, our side. And if you go to this side, you're back to those adorable solar panels. And if you, let's see, I want to go down to this solar system view. So this is where we're at, super big, and we are somewhere right on the inside in here. Yeah. So you can go in and play around with this, see where we are, see where we're cruising. Again, we are about we are 184 days from landing, just under 184 days from landing. So we're literally just hanging out, flying through the vacuum of space. Less than every 90 days, we have to power on. So it's not like we're just chilling in a refrigerator the whole time. So we have to power on, we have to cycle some of our instruments and make sure everything is still working. But we're going to be landing on February 18th, which Michael can talk about with the PowerPoint.
We'll do the PowerPoint. Yeah, that works. Okay. All right.
Okay.
Yeah, so we started talking about some of the EDL, entry, descent, and landing, and we'll go over ours specifically. I figured before that, it'd be kind of interesting to cover how we used to land on Mars. You might have the image of MSL and their infamous sky crane maneuver, but we didn't always land as glamorously on Mars. So let's see if this link opens up, and it might take it a second. I'll start loading it. Give it a chance to load, and see if everyone can see the video. So this is part of the mirror missions of Mars Exploration Rover. You'll notice some similarities. I'll maybe pause it so we can kind of explain along the way. What you just saw separate, that's kind of in that bottom corner. That's that cruise stage with the solar panels and some other propulsive elements. Along the way you have some trajectory correction maneuvers. We're shooting from pretty far to hit a really small target. So along the way you kind of got to course correct. You'd enter, we saw the heat shield. Mars atmosphere is just annoying enough that you have to take it into consideration because things will heat up as you come in really fast and you brush against those CO2 molecules. So you can't design without them. That's why we have that heat shield. You're still going pretty fast. The heat shield does slow you down, but eventually you open up a parachute to slow down even further. It does slow you down, which is the first idea. The second one is that allows you to separate the heat shield now, which you can kind of see. And for MIR specifically, you can have this ball-looking thing on a tether. You're still going pretty fast because remember the atmosphere is just dense enough you have got to consider it, but it's still thin enough that it won't slow you down. So you need these little rocket engines that you just see coming in. And the funny thing is, these are solid rocket engines, so they don't turn off. So you got to make them long enough that they slow you down, but you can't make them burn too long, otherwise you might go back up. So they knew they were going to come in with quite the speed, and they came up with this sort of airbag bouncy ball design, which is, kind of hilarious today, not very subtle. It's a very coarse mechanism. But part of the interesting design behind it is that, you're bouncing all over the place, you're rotating. How are you going to know what side you're going to open up on? And they got this pretty ingenious sort of triple pedal design such that no matter which side it lands on, you wouldn't stay balanced if you're on the tip, so you land on one of the flat sides. And just like that, the panels push you into position. All three of them open up, and there you have a rover on Mars. I'll let it play because we got some pretty cool solar panel unfolding, and that's always pretty fun to see the mass cam kind of come up and swivel into position. But that's pretty much how we used to think of entry, descent, and landing. And you might have seen some of it through MSL, which uses a different technique called the sky crane, which is what we're going to use this time around. And we're going to run through that because we made some improvements since even compared to MSL, and those are pretty important. So there you go, a little mass and a little antenna go into place, and it's pretty cute. And there we go, smile. All right. So I think that one is probably already open, so we'll just jump in to the Mars 2020. And I think this opens up here. All right, so we got this pretty cool animation. So sort of very similar concept, why reinvent the wheel? Sometimes it makes sense to do something that works. So we'll separate from that crew stage, which are our solar panel and some of the propulsion system to keep adjusting the trajectory as we go, because we're on the fast track, about an 8-month journey, but does require some correction along the way. Eventually, I'm going to scroll, I'm not sure which state it happens. There you go. You start heating up as you hit the heat shield. And the heat shield is, designed very specifically, not just to block the heat, but it's kind of cool. It's actually got a very specific ballistic coefficient so that you're kind of lofting, you're kind of gliding like a bird or like a stone skipping on the water as you're going in through Mars atmosphere. It's showing a very steep approach angle, but in reality, you're coming in fairly shallow. You're really skimming the surface. It's kind of cool. It's a good way to slow you down when you're trying to go from planet to planet. Saves on fuel. That's always good. Always like good fuel saving.
Fuel efficiency.
There you go. So you're burning up, you're slowing down. Eventually, similarly to what we just saw, you'll open up a parachute. There you go, that was sudden. Slowing down a little further, and I think it gives you the speed. So you're still, at this point going 625 miles per hour. You would definitely get a speeding ticket for that. That little drogue provides enough deceleration so that, when you separate, this is allowed to go, the heat shield is allowed to fall faster than you are. Very important because, you're really not there to verify how the maneuver is coming along. We had a great question about how long it takes for the information to get back to Earth, and it's about 7 minutes. So you really don't have time to give any inputs whatsoever. Everything's on autopilot. And the last thing you want is to have this separation occur and for this part of the lander to hit the heat shield. It sounds silly, but it's a good thing to avoid. Now, this is the cool part. You're going to see these little beeps. Really what that means is, we've sent different missions to Mars, and it's easy to think of them as very discontinuous missions. We have the Mars Reconnaissance Orbiter, the MIR missions, Viking, MSL, and they kind of all do. They're very pitched so that you showcase what they're doing special. But we're at a cool stage where they're sort of all coming together. We have a lot of imagery from Mars, and how that's coming together for this mission is that we're now implementing this thing called terrain relative navigation. So really on board the lander, you've got all these maps of Mars that are loaded, and they're using a pretty clever algorithm called a particle filter, where essentially, you don't really know where you're going until you get there, and you're essentially just sampling as you go. And depending on what you pick up, at first you don't really have much information. Time goes on, and hey, we see some elevation, we're above the mountain. As you keep sampling, you eventually get a little more resolution, over which possible two mountains you are. And then eventually you've sampled enough through those. It's also ironically about 7 minutes to do the entry, descent, and landing sequence. You eventually know precisely where you are. And why that's important is because you have obstacles on Mars. You got craters, you got rocks that you need to avoid and maneuver around. And
where we're landing, so we're landing in Jezero Crater, which is something that's been all the hype in the science community for decades. It's where we're most likely, we think, to find biosignatures if they exist. And we haven't been able to send anything there because you can't land in Jezero Crater. It's right on the other side. You got mountains on either side. You have a terrain that you can't exactly predict or you can't land in if your ellipse is so big. But like he was saying, the terrain relative navigation made it possible so that we actually could go to this place, which is why all of the instruments that we have are included on this rover rather than the last one that we sent.
Mm-hmm. Yeah, and exactly, because to give you an idea, when we were landing with Mur, I think that uncertainty zone of where you could land was, I believe, if I'm not getting the numbers wrong, 200 by 100 kilometers, 200 long by 100 wide. MSL was about 100 by 40, 100 long by 40. This, I think, we're bringing into 80 by, or a couple kilometers only. And then the next version after that, which would be for lander and sample retrieval lander, are supposed to be, I think, 100 meters by 20 meters. So they're really shooting for a narrow down ellipse. So this is kind of the cool stage where we're going to try and prove this technology and exactly how close we can get. And then, for the next missions, it'll tie in into even more precise landing, like Molly was saying, because some science sites are very interesting, and access is a big issue. If you only have 1 year on Mars, it might take you a while to go and drive there. So that's, similar to what you saw, going back to Mur missions, you'll see 8 engines turn on, and that's important. I'll get back to in a little bit, but you're kind of coasting. Eventually, you'll start dropping the rover on a tether like you saw before, except instead of having this airbag system, you got a little better control over those engines. Eventually, as you get closer, you turn 4 of them off, and you have a much smoother landing where I guess it's going off screen, but I promise it's going on Mars. And then eventually they cut the tether and fly away for safety reasons. You just want that little descent stage to go away and let the rover be on its own.
I have another question.
Yeah,
if I can interrupt. Those engines that are slowing and actually landing the rover on Mars, what are those engines using? Because wouldn't you be concerned about the rover being damaged by those engines?
Absolutely. That's actually one of my big points for today. So I'm really glad you asked. So they're hydrazine engines. There's some implications there. So it's what we call a monopropellant. It really just uses one liquid as the fuel source, goes over a catalyst bed, and that's how you get your burn and your slowdown. So that's, yeah. And actually, to answer your question, let me show the next video because it'll kind of illustrate some of that. But the answer is absolutely, you are at risk of getting some damage. So I've been looking at a lot of those pictures because that's one of the questions we get in propulsion quite a bit. And I saw that NASA had stitched them together recently, and it looks pretty cool because let's see if we can do full screen. So this is, it's overlapped with the audio of the, I'll just do a little pause so I can explain this real fast. So it's overlapped with the audio from the control room as the stage is descending. So I'll let them talk, maybe intervene or interject, at some different points. But of course, because there's that 7-minute difference, what you see and what you hear happen at different times. So this is what the descent actually looked like from the spacecraft perspective. This is still imagery that was sort of stitched one after the other.
Thrusters have been re-enabled. We will control our attitude on shoot. We are decelerating. Rift mode under our
so that's that heat shield, stage separation. I mean, heat shield separation.
Dynamics phase. Come back again with wrist mode dynamics.
Wrist mode is nominal. We're 9 kilometers and descending.
Active.
Solid range.
Net filter converged with a velocity correction of 0.7 meters a second.
We've acquired the ground with the radar.
An altitude of 8 kilometers.
Regional has separated where we found the ground command zones due to occultation as expected. We're using by to prime the MLE engines in preparation for power flight.
So the MLEs are those engines that we were just talking about,
We're
the
down to
Mars
90
Sniper engines,
seconds
and you're
at
looking
altitude of
straight down,
6.5 kilometers descending.
straight down to the surface, essentially. You can see on that surface, you got some ridges on the bottom right, some craters on the top left. That's the kind of stuff we want to avoid. That's dangerous.
And like Michael was saying, you can't just drop in and drive over. Even though we're a rover, every single wheel rotation is counted.
We're down to 86 meters per second at an altitude of 4 kilometers and descending.
So that says you're pretty much in free
We've
fall.
lost
Eventually,
over
the engines will
time
turn
as
on.
expected. We're continuing on
Turn
altitude
on
telemetry.
a couple hundred meters above the surface, and
Ground solution equals minus 10.8 meters, vertical velocity of minus 80. We are priming 8 meters per second. Start enabled, standing by for fractional
we're
separation.
close to that engine start, and you'll kind of see on the ground. You can actually see
Signal
when they
odyssey
turn
is still
on.
strong.
There's a little lag between what they're saying and what the video actually shows. But you'll kind of see these rings,
We are in power
it's almost like a peanut shape of dust getting thrown off. And when you see it visually, you're still at about 80 meters
About 70 meters per second.
above the surface.
Signal to
Which that's
Austral
like
air.
70 feet, something like that.
500 meters in altitude.
So still got a little ways. Still 500, 1,500
Standing by for
feet
taxi.
roughly.
Constant velocity accordion nominal. Altitude error 5.9 meters. We found a nice
There
flat
you
place.
go. That was the
Coming in
start
ready
of those
for segment.
engines. As you get closer, it gets messier.
Down
They
10 meters per second.
actually
40
turn off
meters
4 of
altitude.
the engines. The engines are mounted at different angles. 4 of them are essentially looking almost straight down. 4 of them are looking a little more outwards. And it's for that exact purpose of trying to move less dust around and train less dust, as we call it, so that you're not
Signal to odyssey remains
recirculating
strong.
that dust. Some,
Tango Delta nominal.
we'll let them get there, the moment of glory.
I won't cry because you guys are watching, but I cried earlier today.
Stable.
There you go, and you can kind of see that speck of light coming from under the rover. This is from the Marty camera.
UHF is good.
Camera filming all of that.
Touchdown confirmed. Receiving.
Very excited engineers because they, probably put a decade of work
Did
into
some
it.
cool
so,
stuff.
Yeah. So some of those engines were mounted at different angles, and the idea was to, there's sort of 3 main problems. One is you can throw a lot of rocks and pebbles, and some instruments actually got damaged on MSL because of that. Another aspect is that you are kicking up dust in an environment that has a fairly low gravity, and some of those dust particles are fairly light, so they're going to get suspended and just kind of hang out in the air for a long time. And what you don't want is to then open your solar panels and have that dust settle on top of them and prevent you from getting the power that you need, because we're pretty far from the sun at that point. And the other problem is, for example, when you come in on Mars, you saw the camera, the spacecraft actually isn't looking for a camera, it's looking for a radar system. Eventually, when the engines turn on and there's so much dust that gets kicked up, you can't really see the terrain anymore, and you switch to a laser ranging system. It has a lot less resolution, which is why for a long time that uncertainty zone of where you land was quite large, because you turn on the engines pretty high up, and as you saw, the dust moves around from pretty high up. So you switch to that system so you can kind of still tell how close you are, because you need to know when you're cutting that umbilical cord and flying away and leaving the rover on the ground. But that's sort of like the 3 main problems that we encounter with that. And if we want to tie into hardships that we encounter, and Molly will talk about some of them. Of course, there's that's the one that I like because it's sort of in between engineering and science. It is a problem that engineers encounter because they need to fix it, but the way you want to fix it sometimes goes against what science would like to do. On the propulsion side, you might want to use a bipropellant that combines an oxidizer and a fuel, because those engines can be a little more efficient, but then you create, because you had asked about the fuel, the nice thing with hydrazine is that it decomposes in a very predictable way. So the science team, when they sample and trying to figure out what are the rocks made of, you know you're going to have some trace elements of the fuel that you dropped on the surface. It's less of a problem for a rover because we can roll over and go to another place. But for a lander like InSight that landed recently, or a lander like Europa Lander, if you're stuck in that same zone where you landed and you had fuel on the surface, it's easier if you can predict what that fuel is. Whereas if you have some Viper pumps, they generate a lot of different hydrocarbons, and we're there to try and find biosignatures, which are hydrocarbons. So you make a very noisy signal, and your job just got a whole lot harder. So it's science can have other priorities than engineering sometimes, also because you could damage science equipment. So it's actually one of the biggest questions we're facing of how to solve these problems when we're landing on other planetary bodies. Is how do you stop stuff from moving around, if at all possible? And some planets might have denser atmospheres, and other solutions might be better. But it's a very interesting question that's right, in between science and engineering, but both need to be heavily concerned about it. So that's one of the hardships we have, and probably one of the requests we get the most at JPL is, people who come to us and say, hey, we want to land. What do we think is going to happen? And to tie it into the next mission, and I think Molly will give a little more of an overview on sample retrieval, we're going to be dropping samples. And so, that dust could also cover those samples when we come in to land to find them. We want to land close once again, which is why that uncertainty zone needs to be small, so you don't have to drive a long distance to go get them. But if you land too close, you could kick up dust and cover the sample you're trying to find. And then, if you can't find it because it all looks like sand, that's becomes very challenging.
Yeah, come in and land on your samples or something.
Yeah, exactly.
Smash. So there is this little picture on the left side. So this mission is the first step in Mars sample return mission. So to boil all of it down, which is decades of people's work, into like 2 sentences, our rover is going to go collect samples and try and find places where we should be collecting samples, and where we should be looking. Next step is, and so that's this right here. So we're going to take samples, we're going to cache them away. Next step is we're going to have a sample return lander, which is a base. And then we're going to have a Mars Ascent vehicle, which is like a fancy basketball. We're going to put all the cache samples into the Mars Ascent vehicle, and then we're going to launch them up. And then another spacecraft, a sample return orbiter, is going to swing by and pick it up as we throw it. So very fancy space basketball to take and return samples. And this is the mission that people have been talking about, again, for decades, where we're trying to bring back samples to Earth so that we can do a full analysis, because the instruments, and I'll go over some of them. Oops, what have I done? Okay. The instruments that we have a lot on board. So we have the best laboratory that we can put on another planet, but that's still a laboratory that we're putting on another planet. So something that we've experienced in the past is, to try and understand the chemistry in some of these rocks, you have to pulverize the rocks and then send them through your analyzer. And in pulverizing the rock, you lose a lot of information. So again, the main point is we want to bring samples back so that engineers with thumbs can go through and start analyzing these samples. What we have on the rover is, again, hopefully the best thing that we can have when we're up there. We have a lot. I'm not going to go over each of them because, as all of you know, I'm sure I have a favorite one, the one that I worked on, Sherlock. But there's so much information. If you have time, go read about each of these instruments. They're going to change the world. But we have, as a general overview, we have some instruments that are built on hardware from the past. So this whole rover was supposed to be a build to print. So that means we took the schematics from MSL that launched in 2012, and we're using them to build this rover. And we hit a lot of hiccups along the way. We learned a lot about how to write proper test procedures, how to write anything, like those kinds of things, to make sure that all of your notes are captured. And it's something 589 does, well, and something that we're continuing to improve on is to record, so every year you learn something new, put it in your big blue book, put it in your CAD files, put it in whatever, and make it so that the next round of students knows what they're working with and knows what you guys have done, so you don't have to reinvent the wheel every time. So we took the main idea of the last rover that we sent, and we just gave it like a total upgrade. So the first upgrade, something that isn't listed as an instrument, but a lesson learned, is the wheels that we have on here. What we saw on MSL was that we had tiny little triangles, that were supposed to help us not slip as we went around and drove around. What we found was that those were points of failure. So as we would drive around, we hit a little rock and push it through. So now MSL wheels are kind of like tattered and gross. They're just not doing very well. So what we did was we took those lessons as we can apply them, and we updated the wheels. The other updates that we have are, we actually switched out these instruments for newer things. So we have RimFax, which is a radar imager for Mars subsurface experiment. SuperCam, that one is very similar to some of the other instruments that were on MSL. MathCamZ, and just as a preface, the theme of this rover is cameras. Like Michael was saying, we have cameras to see the ground as we land. We have cameras to see the air around us. We have cameras every place you look. These two cameras right here on MathCamZ, those are supposed to be so we can give the rover depth perception. So we can actually, look at where we're going and kind of get a better idea than we've had before. We have the META, which is the Mars Environmental Dynamics Analyzer. Again, just going to focus on the coolest one in my opinion, which is, first one special shout out to the helicopter. Helicopter holds a special place in many people's hearts. It's going to be a super, super cool thing. It's going to show us if we can, it's going to be the first test of powered flight on another planet. And it's absolutely insane to think about a helicopter on another planet, because a helicopter, you need a lot of air to move around so that you can lift your heavy weight. And the density of the Martian atmosphere is less than 1% of what we have here on Earth. So we have these giant wings that spin super, super fast, and we're literally carrying around like a battery pack and a GoPro is what the helicopter is. So it's going to do some awesome, showing what we have the ability to do. Yeah, it's going to be super, super cool. And today is National Aviation Day, so kind of fitting that we spend some time focusing around helicopter. Okay, so again, a lot of the instruments that we have on here. This one, Sherlock, is the one that I worked on. It's a spectrometer that uses Raman spectrometry. Raman it's just a wavelength that you look at specifically. What we're going to do is we're going to take our camera and we're going to take a picture of the rock. Our camera is called Watson. I can't tell you what the acronym is, but it's online. So we have a camera. We'll take a picture of a rock, and then we'll use our laser to shoot at the ground, and then we'll read the luminescence that comes back. What that's going to tell us is if there are any biosignatures in the ground. And how we do that is all of that coding that I hate so much. We had the engineers and the scientists here develop this data package. So what we're going to do is we're going to collect a bunch of spectrometry data, and then we're going to compare it to the library that they've created, and their software is going to run it through and see, when you have these compounds. And it's not like you have, like in a chemistry lab where you do spectrometry and you have one sample, just one sample. It's, if there was life there, then you have a bunch of stuff that's likely layered on top of each other. And so trying to find a way to untangle your data is just insane. so what the laser does, and I worked on a few parts of it, but the most difficult and the reason I missed so many robotic sessions was because of the laser power supply. What the laser is going to do is it's going to look at a larger area and a smaller area, and it's going to give two different types of samples, two different types of luminescence data. And then the scientists and engineers down here are going to compare that and see what kind of biosignatures of what we would expect are in there. So we're like 5 minutes in, 5 minutes from the end. So that's enough of the instruments. And again, this is from KSC. This is what we're headed towards. And I think that's the end. So yeah, go Mars. I don't know if there are questions or anything in time that's remaining.
We can definitely go over the hour. So if anyone has questions, don't be afraid to ask them. You can type it out.
So ramen, not like the noodles?
Not like the noodles. No, I definitely ate a good amount of ramen noodles while working on it just because, but not as fun.
It'd be pretty great to have ramen on Mars.
Yeah.
One day when we send people, we might actually have that.
We're going to look for ramen on Mars.
Just that water.
Yeah. Cool.
All right.
Hey, Molly and Michael. I have a question for you guys. So I have spent some time at the lab, and I know what it's like, and it's a fun time to work at JPL. But you know, I feel like for a lot of people who are still in high school, working at a place like NASA sounds so tremendously exciting and yet overwhelming that they can probably feel like there's no way they'll ever make it. And I certainly felt like that too when I was in high school. Do you have any advice for people who actually would like to work on stuff like you have?
Sure, yeah. So for me, that came through being really involved with the rocket propulsion lab, kind of like you would be with FIRST Robotics. There's a lot of people who just, love science and robots, or where I was, it was rockets, people that might have connections to JPL and or NASA that might, one day recognize how eagerly you want to work there and bring you into the fold. Internships also worked out pretty well for me. I would say, don't be afraid to be bold. Like you said, it does seem overwhelming. I guess official application systems can be kind of a black box. You send a resume in, you never really know what's going to come back. So, I would always say, don't be afraid to be bold and call people and just say, hey, I'm interested, kind of find them on LinkedIn. Some of them have their email, feel free to sort of cold call or cold email people and reach out. You might be surprised sometimes, there are people who are fascinated by science, and a lot of times they might need help. You're working on a project, you're trying to do a million things. You might be thinking, hey, I would love to have a summer intern. And, so don't be afraid to sort of like circumnavigate the official process and just reach out to people who are passionate with what they do and who might want to share that passion by taking someone on for the summer or school year.
Yeah.
Like that.
And I think I have a different start, but the same ending. I was a bad college student. I had a really, really, really hard time in college. And not because I didn't like classes or because I didn't like physics or anything, but, life gets in the way often. So I think it's important, and something that I've learned more after being at JPL. It took me a while to learn, but it's okay to not be the most confident in a room. It's okay to, not be 100% motivated all the time. That doesn't mean that you failed. But I do think, like Michael was saying, in my case, I would not get an internship. Like, I was not the most stellar student of anyone ever. But I happened to be asking for help at the same, and I had, luckily, I I knew how to operate the systems that they were using. So when I was in college, I learned everything that I could. I went way out of my comfort zone, out of my field, into environmental science, because it was something that I was really passionate about. And by following that passion, it led me to JPL. But it was, like Michael was saying, I called Lynn, I called my mom, I called, other people. And since then, since some of my confidence has come back, anytime I need something, I'm on the phone. Like, use your network, use your resources. And even more important than that sometimes is answer your phone, which I know Brian and everyone is going to laugh about because I never, ever answer my phone. But meaning, when someone asks for help, help them. So if there's anything that you can do to help your fellow humans, do it, and the world will pay you back.
On that note, calling is definitely much better than texting because it does get faster responses.
Yes, I suck. Don't ever try to text me, please.
Yeah, but that's very true. And if I can add one thing too, like Molly was saying, learn different skills. If you are passionate with multiple fields of science, don't hesitate to be unique and combine them. Don't feel like you have to stick to one prescribed curriculum. And go ahead and combine different things if you are interested by multiple areas. Part of why I ended up in propulsion was because I liked both the engineering and the chemistry, and they just happened to need someone who could do materials chemistry and propulsion, but everyone in our group is a very engineering-only training type of background. So, it could really play in your favor. You'll learn cool skills along the way that someone might need, and if anything, you just become, someone who has learned more cool things in life. Science is pretty fun that way, and it's good to broaden your horizon and just have different perspectives on what might be the same problem, just viewed from a different kind of science. And it might actually also translate to good internship or job prospects later.
And to add, it's super, super helpful to go outside of your field. I think I've used not more from my other classes than I have from my physics classes, but to have a little bit of coding experience, even though it's incredibly difficult, and I admire all of you, you need to have a little bit of coding. You need to go to math class. Even if you hate it, you have to at least go. You have to take an English class. If you think that's a lie and you were like me and you didn't ever want to take English or history again, get over yourself, take an English class. Writing is more important than anything. Build yourself as a person and follow the things that you like to do, because when employers are looking for people, they're not everybody, but in my experience, when employers are looking for people, they're looking for people that are going to be excited about the work that they're doing. And luckily I was just born as a puppy, so I'm excited about everything, but. Yeah.
I have a question. So have you guys tested bouncing a giant Mars robot off the ground with balloons? Because that seems pretty epic. I want to know if that's been tested before.
So surprise, that was done twice. That was actually what we did. That delivery system, we bounced it and it rolled. And so yes, there was everything that we do is tested. So we have a
drop towers.
Yeah.
Okay, that's awesome. Because I remember Nito had this one Wednesday project where we try and drop an egg and make sure it doesn't crack or explode. So it reminded me of that.
Yeah.
And we have a JPL, a pretty cool formulation office as well that is always
some pretty cool people.
Always looking for concepts. We went for that airbag method, but there are people looking at, what could we do on Mars? We got the helicopter, but before we converged on that, people were looking at sort of a Zeppelin hot air balloon type setup, different mortars system, if you can just kind of launch something on Mars. Not necessarily to go in orbit, but just to cover a longer range, different little gliders. There's lots of cool concepts that come up with. Only a few make it to the public stage where we, can make it put on a mission. if we could put all the instruments, we would happily just, you know, put
Scientists
all of
everywhere.
this concept. But yeah, there's some pretty cool concepts out there. So.
And a cool thing that JPL does is they have, they do break things into stages very well. So you have the crazy mad scientists that just like come up with these crazy ideas, and they go to a team and the team tries to develop them, and then they go to another team, they try to develop them, and you know, the paths that you can take, and then there's different levels. So you can say like, oh, we're going to give you a tiny amount of money and you get to make a tiny test and see if it works. So it's like a prototype. And then, you know, once you have your prototype tested and shown that it works, then you can move on to the, you know, like the stage that people see, the public stage.
And on that note too, the first drawing for the sky crane maneuver that we have used or about to use for the second time, possibly the third, started off on a napkin. There's two people talking and brainstorming. So it's kind of cool to see that.
Yeah, that's awesome.
You can go from that crazy of a concept to, you know, tons of engineering drawings.
Thank you.
Yeah.
So I was actually wondering, since there's such a great difference between the density of the atmosphere on Earth and Mars, how exactly was the helicopter tested? Was it tested like in a vacuum or close to vacuum?
So the short answer was it was tested in everything. So JPL has this really awesome space simulator, which is a giant room that they can take down to vacuum, they can take to whatever they need. So they made it simulate a Martian environment, and then they flew it in there. So there were a lot of like piece part tests, you know, like how we were talking last season about, you know, you can test little parts of the robot before integrating the whole thing together. And that's kind of how they do it. They have different parts that they test, but eventually we make the space at JPL.
Great, thank you.
Yeah.
Hello, Molly and Michael. Great presentation. Thank you. This is Antonio. I'm just curious to see, to know how many people work at JPL on this project. How many people are working now that is on his way to Mars?
So I think it's 6,000 people on lab. Of course, not all of them working on MSL. I think the MSL was 3,000, close to 3,000 people.
Yeah.
Half,
2020, yeah.
Yeah, half of which are JPL, half of which are some of our commercial partners, Lockheed and other companies we partner with. You know, we do a lot of integrations. So some of those parts are built in-house. Some are built all over the US or even abroad. Some of the science instruments were in France and Toulouse. And eventually it all comes back to JPL, gets integrated and sent to the Cape where we sell that launch.
Yeah, and now we have, so kind of how the workforce has changed. Again, with how JPL breaks it down, we have phases of missions. So phase A is when you first start. Phase D is when you're packing everything up and doing ATLA work. And then phase E is where you're launching and doing science ops. And so our phase E is, I'm not sure exactly how many people, but I know that you lose all of the engineers that were on your instruments and build team, and you just maintain your operations group. So that would be on the order of hundreds, not thousands.
Thank you.
So we had a question in the comments. Could you suggest ways 589 can better capture lessons learned and also deal with information and knowledge management?
Oh my God. I don't know who wrote this because I don't have the comments open, but I love you. Do you want to go first?
On lessons learned? Or?
Yeah, like how do we capture, okay, so how do we capture lessons learned in 589? And that's something, because, you know, you guys cycle every 4 years, there's always some kind of everything. I think first step is acceptance. We aren't going to capture everything. And for like the type A people like me, that's going to be really bothersome. But we won't capture everything. But if you have your CAD files, finding a way to store them. I think we already have, and Brian or Lynn or Thomas, correct me, we already have GitHub storage for some of our documents.
We do for, I think we just set it up last year, so we probably only have 1 year of code saved. The kids could probably correct me, and I think everything else, previous years was just a Google Drive folder, so it's hard to say if it's complete or not.
Right.
So
I think something that, at least something that I've seen in my very, very short career is that it's important to collect the lessons learned, but it's very important to make sure that those are available for everybody to see. So I think something that we can do, depending on how we're able to do it, is if you're part of the electronics group, then write down what you know and write down the things that like burned you, not actually burned on electronics, but write down the things that you found out along the way so that the next student doesn't have to find it out. And just keep a log, like what we did on Sherlock, and what Mars 2020 is doing is they ask every project manager to submit a lessons learned report. And so like they reached out to us and we said, okay, on the laser power supply, we learned this, and on the power distribution unit, we learned this, and that kind of stuff. And then that all gets stored as like a final report.
Sorry, go ahead.
I'm sorry, I wanted to add one thing to what Molly just said. At this level with the robotics team, if there's something that confused you throughout the season and it just kind of got solved but not explained, you can write down your questions too. And when you come back to it the next year, if you still don't know, you can, you don't know. So now you can ask the right questions and hopefully get it explained. Or it can be something we come to during the off season and say, hey, if someone doesn't know, then more people don't know, and we can cover it and teach it. So write down everything.
Yeah. To bounce off what both you, Ryan, and Molly were saying, definitely in terms of lessons learned, if you can document what you have, especially at the end, it's tempting when you've had, especially if you had a good season, to want to celebrate or move on to something else, Don't forget to keep some time. It sounds a little boring and dry, but on some of the more recent projects at JPL, we've had some pretty good management that's given us, up to a month where they say, hey, focus on documenting everything you've done. So it doesn't interfere necessarily with, you trying to get the engineering done, but your role is really to, contribute to that heritage in a way that when people come back to it, they can have documents that are, clear. Sometimes it's easier to write them at the end because you do go for a lot of iterations. Things are stressful during the year, so it's not always easy and practical to do it as you go. It does save you time, but sometimes in practice it's hard. But try and document after the season's over when you kind of have a cool head and you see what worked, what didn't. And if you can, like you were saying, Brian, to write down questions, keep your alum close because they've worked on those. And then, sometimes devil's in the details. You might be spinning around thinking, oh, well, what value did they use for this code or that? But sometimes, it's a simple question that could be easily answered by an alum. They might be able to tell you, well, press the F11 key, not F8. And that could be very useful. Even at work, sometimes we'll really go talk to one of the elders, I guess, for lack of a better word, a senior engineer who might have been there at that time and knows what the thought process was behind that decision, stuff like that too. So.
And it's really important to remember that you aren't writing these notes for yourself. You're writing these notes for the next generation and the generation after that and everything. So in JPL, it's like a game of telephone. Someone writes a note, they leave like everything is a 3-letter acronym, and you have no idea what they're actually talking about. And on 589, we've seen in the past a couple times where, people go to leave, comments or something, or how we name files. This is going to sound like, grandma, like get off my lawn kind of thing. But when you're in those moments, when you're creating file names, when you're adding in data, things like that, that's the time to not be silly, because that's very important. I know in something that we joke about at work is that, the file name is like V1-2 February of 1963, it leads you to nowhere. And if you have either inside jokes in your code or you have 3-letter acronyms, whatever it is, the next generation isn't going to know, and they're just going to be stuck without your notes. So just be serious when you take notes. off my grandma soapbox now.
Sam, do you have something?
Nothing. I just agree so much, like 1,000,000,000%. Grandma soapbox all day. You can have humor in your naming of things, but you should also make sure that things are to be understood.
Right.
And about like not writing things for yourself. You're not writing things for yourself now, but you're writing things maybe for yourself like 6 months from now, and will not remember, right?
Mm-hmm.
Definitely times where present Michael has thanked past Michael for commenting code appropriately, even though it was late at night.
And one of my first introductions to coding Michael was when he was reading someone else's code and they didn't have comments. And this jovial man was not quite so happy.
Brings up the dark side.
All right, let's wrap up with one last question, which is very, very current affairs. I don't feel you got to talk too much about it, but working from home and the students all had their first day of class. If they're at CV, they had their first day of class today, and no one really expects to still be doing school or work from home. So any quick lessons that you two have learned over the last few months that you think would be good for everyone to know?
Could give a whole presentation on working from home. You want to go?
If you want to go for it.
So, okay. So this is also an insight into my personality as well as a statement. When we start, so we've been working from home since March 19th. And it's, at first, it was super awesome. Like, I get to work from home. I can go get snacks whenever I want. My dog is right next to me. Like, life is so good. And it really was. Like, my productivity was way, way, way up. So, lesson, take advantage of that productivity and get everything done that you can. Because there are going to be days when it just sucks. Like, it sucks so bad. And it's important to recognize that, you don't have to have a good day every day. So if you're having a bad day, do what you can, make short goals, I keep a notebook. I'm like debating whether I show it to you or not. It's kind of crazy, but I keep a notebook, and every day I write down the tasks that I have to do that day, and I go through and I cross them off. And that's, again, the type A that I've carried with me my whole life, but it's so, so important because there are going to be days when it really sucks. And working from home, like, your motivation is just sideways and weird. And like, I miss my cube mate. Her name is Jackie. She is the sweetest, loveliest human. We have plans together. It's great. And not seeing her and not seeing the people from work, it's tough sometimes. Like, it's really, really tough. So everyone should download House Party, the app. Download House Party and play with your friends. It's super fun. There are games. There's like guacamole challenges. Do it. And also, so be social as much as you can. Don't let your own drive you into the ground. It's okay to have bad days. Just communicate with those around you. And try as best as you can to be strict. So again, back on that grandma soapbox, if you can keep a schedule, keep a schedule. Like, no one's going to tell you that you have to eat at this time. There are no more bells that are going to tell you what you're doing, what you're not doing. So keep a schedule, keep a to-do list, talk to people. Don't go out to any of the parties that I'm reading about on the news.
Yeah.
Don't do it.
Yeah, I think pretty similarly. I like the flexibility of working from home in the sense that, different people might have different work styles or different productivity peaks. So, of course, you still have to be available for your colleagues, you can have an obligation. But, if you're more productive earlier in the morning or later at night, you kind of have some flexibility there that allows you to also tailor it a little bit to how you work best. But again, along the lines of what Molly was saying, what helped me was also sticking to a routine. Otherwise days kind of become a blur. So kind of, still living as if you were about to go out, go to school, wake up, whether it's a workout or reading or whatever it is you do. Get ready as if you were gonna go out. Don't just stay in.
Wear
bathrobes.
pants.
Yeah.
Don't walk around in pajamas every day.
Bathrobes, pajamas, whatever it is. It's commit to a routine as if you were about to go out in the social world, and definitely stay in touch. I mean, we still have happy hour Zoom parties with colleagues, so that you don't just get to interact with them on the phone or video chat for work purposes. You also take some time to still socialize, especially these days, because it's kind of the interaction becomes all the more important. But the flexibility was a nice aspect to it.
And I was super self-conscious when we started the whole work from home, and I had to turn on a webcam with people that I work with. That was it's still super weird. I'm not into this vibe. But do it if you can. Have your webcam on, make sure you're wearing clothes, have your webcam on, and then, it adds a little bit of personality back. So it's important.
We've had people having fun with it. We're just, I don't know, setting up fun, friendly posters in the background, or just showcasing what they like, or their pets at home. We've had some pretty fun moments.
Hawaiian shirt meetings.
Yeah,
that's
exactly.
A thing, so.
Make it a theme.
Yeah.
All right, well, thank you, both Molly and Michael, for giving us your time today. I gave you a difficult task of presenting together, but you guys did great, handled it just fine. Some quick announcements for the 589ers and anyone else we are inviting. I have lost track. We have one more talk in the summer series. It is I am presenting Save the Best for Last. That will be in 2 weeks on September 2nd. And I will be posting some information on Discord tonight or tomorrow regarding it. And you'll probably receive an email about it from Mrs. Martos as well. So yeah, be on the lookout for that. And then we'll take a break, and you also expect a survey of some sort, just so that we can kind of gauge your interest for the fall on what we might possibly offer. So yeah, be on the lookout for that. Again, thank you, Molly and Michael. It was great.
Thanks for having us.